right. Hello, class. So today we're going to try and record a bit of lecture on system properties. And, well, I guess the main contribution today, as opposed to lecture 4, is that we're going to be introducing inputs. X dot equals AX. That's what we had last time. And now we're going to be adding one little additional term, BU, here. This is not to be trivialized, however, because last time when we had x dot equals AX, we were only looking at sort of the map of system properties between the initial condition and the state. And today we'll be looking at the relationship between U, which is a function of time, a signal, not a vector. It's a vector here. The U is also a vector, or U of t is a vector, right? Right, but we're not going to be thinking about it that way. So we're going to get rid of the U of t, and if we like, we can do U dot, right? Just to indicate that this is a function of time. So we have an input, a signal, which varies with time. At every instant in time, of course, it's a vector. But we have infinitely more information than we had to map from than we had in the case of a vector, right? This is a signal. Right, so not only do we have U of t, or say U of 0, which is a normal vector, we have U at every other time greater than t. Greater than 0. So it's a much more complicated map. Right. So remember the framework we sort of introduced in the previous lecture, which was, right, we've got sort of different hierarchies of what we're looking for. So we've got the system itself, right, x dot equals AX plus BU now. So that's one representation of the system. We have the system representation, or the system itself, right? What's going on inside. And on top of that, right, we have an alternative way of viewing the system, where the system itself is a black box. We don't really care what's going on inside of it. Where it's a map from this input, this signal space, to an output. Well, what's our output in this case? Well, we don't have an output quite yet. We'll get to that in the next lecture. At this point in time, our output is x of t. Right. So it's also a signal. It's not the vector x of t. It's x of t at every time, right? So it's a signal itself, right? So we're going to make that a signal. And then to indicate that remind us, so to speak, that it's a signal, we'll put a little dot there, right, to indicate that we need to know that it's a map from U at every time to X at every time, right? It's not, excuse me. Sorry about that. I just had to turn off the AC so it doesn't make noise. All right, so it's a map from a function of time, right? Maybe that's our U of t, to another function of time. That's maybe our x of t. Right? So it's a map of a function to a function. So that's much more complicated, right? This input-output relationship. So there's two. So we have this relationship between inputs and outputs, the properties of this relationship. And then, of course, so we'll sort of tier that hierarchy there. And then next, of course, we have sort of what we can say about these properties using the properties of the system representation. So we've got the representation. And the representation, by that we mean A and B, those two matrices. So this is a very simple representation, right? It's like just two matrices. We don't have to fuss about it too much. Right, but what can we say about these other things? The properties of the map. And, well, we'll sort of mostly ignore this first hierarchy up here for the most part. What can we say about the properties of the input to output map given properties of these two matrices, A and B? And then, of course, what we're really interested in is optimization. So how can we relate the properties of, say, this input-output relationship using positive matrices? So we'll put that under optimization. And in particular, is there a positive matrix which allows us to characterize properties of this relationship, right? This particular point, this positive matrix. And remember, we talked about how we could encapsulate properties of the system representations using Lyapunov functions. And so typically these positive matrices represent Lyapunov functions. X transpose PX. Right. So we'll take this optimization problem and we'll represent it using, or we'll interpret it in terms of the search for a Lyapunov function. And these Lyapunov functions, as we argued, right, will allow us to tell us properties of the system itself. Now, where does that leave this representation, A and B? Well, of course, the representation will inform the optimization problem. So there has to be some relationship between the system, right, and our Lyapunov function so that it captures properties of the system. And so the representation will go into the optimization problem, which allows us to express the search for a Lyapunov function, which allows us to identify properties of the system. So very sort of complicated mapping of things going everywhere. But I hope this interpretation will inform sort of the discussion of what we're doing here in this lecture. All right. So this is a recall slide, meaning this is stuff we already learned. So in particular, this for stability, right? This is the map, remember, from initial condition to, well, really an initial condition to the solution of the system, right? So basically, this is our optimization problem. And it's informed, of course, by the system representation, those two A matrices. And the solution to this Lyapunov function, well, we want it to be negative definite, but we can just say strictly less than 0 equals some, well, it has to be definite in some sense, right? So the solution, right, A transpose P plus PA equals negative Q. Well, Q gives us the core of this Lyapunov function. There's our core, which is encapsulates the system properties, right? The solution map, if you will, from state to signal. And then the integral transforms that solution to a property. In this case, we're looking at the size of the solution. So that's the integral of x of t dt from 0 to infinity. So the size of the solution remaining, so to speak, from that initial condition, that follows from that initial condition. So if this is our solution, right, it's just the integral of that line. All right, and we had an equivalent for discrete time systems, of course, as well. right? And that also gave us a Lyapunov function, which also interpreted as the solution, because the solution here was x of k equals a to the k, x 0. So we're going to extend this framework a little bit now to input-output systems. Last time, of course, we talked a little bit about the eigenvalues of A and how those eigenvalues could be represented as system properties using these types of Lyapunov functions. We didn't actually derive them for the Chilali and Gahene and the other result, but we you can get the picture, right? It's some variation of these two Lyapunov functions. Right. That gives us those eigenvalue properties. Right. So if we're going to look for system properties, right? Here's our system. Here it's a black box, right? At the system level, the system property level, it's a black box. Right. So what we really care about is not some internal state, x of t, right? Well, we do care about that because that, in fact, is our output at this point. In principle, we don't care about whatever's going on inside that black box. We really care about the map from this signal, which is a function of time, to this signal, which is also a function of time. Right. And so as for the states, the stability problem, where we solved the solution, we found an explicit expression for the solution. In this case, we're also going to find an explicit expression for the output of the system given the input of the system. Right? So a map between this input here, here, and here, to the output of the system, which is y of t. Right? So in this lecture, we're not going to actually be concerned too much with y because we're not going to introduce the C and the D matrices quite yet. But so we'll mostly be focusing on this map. But the difference between this map right here, right, and this map is almost trivial. So specifically, right, if you just, right, I mean, y equals cx plus du, if we just plug in x of t into that expression, right, then, right, we get a new solution for y, right. So that's, so once we get this, once we have this, this is also follows almost trivially. Okay. So this is the solution. I'm not, unlike in the previous lecture, I'm not going to derive it. It's not hard to derive, right? Once you have the answer, in this case, it's relatively easy to prove that it is the answer, right? It's just a matter of differentiation, right? If you look at this little term here, right? And if you differentiate it with respect to time, right? Well, what happens? Well, you got to use this Leibniz rule for differentiation of integrals, which is a very useful mathematical fact, I guess, for differentiation of integrals. And basically what it says is that when you differentiate something like this with respect to t, which has a t in the integral and a t in the integrand, right? So this is integrand, this is integral. Or it has a t in the limits of the integral, I should say. Right? Then you differentiate twice. You basically differentiate once with respect to the integrand, and then you differentiate once with respect to the integral, or the limits of the integral. And of course dt of t, right, is just 1, and dt of 0 is just 0. And so you get two terms. You get just the thing itself, which is, of course, right, x of t, right? And then you get a plus term, which is the differentiation of this. So it's relatively easy to verify. There's two parts to this, right? So, okay, how do we do that? Well, I'm not going to go over the details. I'm afraid you have to take my word for it. It's relatively easy to prove on your own, but it's not like I assign it for a homework or anything like that, so don't worry. Although if you want to, sure, go for it. So in any case, what this gives us in the end, if we now erase all this rubbish, which I've written all over the place, right, is a map from our inputs, u of t here, to our output signal, y of t, where x, in fact, does not appear anywhere. Let's cross that bit out. Right, so we can express y of t here in terms of u of t here without x ever appearing in the expression. Right? So this is the ideal sort of way to represent your input to output map. Something that does not involve anything that's going on in this interior of the box. Right? We don't care what's going on in the interior of the box. We only care what the relationship is between the inputs and the outputs. And so in this lecture, we're focusing on control, stabilization, and controllability, basically. And so the question becomes, right, does there exist a u of t, which will stabilize the system? And again, we're not going to focus on y, we're just going to focus on x in this particular case, right? First, right, is there an input which will drive us to 0, which will sort of stabilize the state to 0? And then second, in a highly related question, right, if we have a state that we'd like to get to, right, is there an input which will drive us there? So if there's a desired target, right, so here's our initial condition, say, which is 0, and I'll mention this important information in just a second. Oops, I guess that doesn't work very well. Let's see, change our color here. All right. Right. So for a given initial condition, right, x of 0, or x of 0 equals 0 in this case, and for a desired final state, say, I don't know, 10 step input, for example, x of t, say x of 10 maybe, x of 10 equals 1, is there an input, u of t, which will drive us from that initial condition, maybe taking some long thing, over there to our desired state. So this is another notion of controllability, which we'll talk about. And then, so we don't, in this case, we don't care how we get there. We just care that we get there. And then in the second half of this lecture, we're going to come back to this question of, well, what form that input should take. Now, at this point, I should make an important distinction between a control input and a controller. So what we're going to be talking about the first half of this lecture is a control input. All right, which is whatever the signal you want to give the system to make it do what you want. Well, that's often thought of as open loop control, in the sense that we assume we know exactly where we started, 0 in this case, and we can determine a priori the exact input which will drive us there. Right? This works very good in theory. In practice, however, there's some issues with it. Robustness, models are all wrong, noise, uncertainty or initial condition, and so forth. All right. So in the second half of the lecture, we're going to be talking more about whether we can structure this input in the form of a controller. And this is what I would call a controller. Something which maps sort of your current state, which you sensed input or sensed state, wherever you are, you know, with say noisy measurements or whatever, to the signal which is going to drive you towards your desired destination. So current input signal, I guess I should call it. Current controlled input. Okay. So we'll make that distinction later in the lecture. Okay. Of course, for discrete time systems, we have a similar thing. Oh, by the way, I said I was going to emphasize this point. The initial condition, right? I mentioned briefly, right, your initial condition here. When we talk about input to output properties, right, we would like to get rid of whatever's going on in the black box, right? Remember here, we don't care what x of t is. Well, how do we square that with the initial condition? Well, in almost I don't think it comes up at all, in fact, in the entire rest of this course, basically. Well, no, when we get to nonlinear stability, there's a different thing. But in the entire first half of this course, let's say, we're basically going to assume that the initial condition is 0, that the unperturbed system state is 0. And that is important because it allows us to differentiate the system properties from whatever's going on internally to the system, because that initial condition is impossible to really measure. And so hence, of course, this issue of robustness, right? The controller becomes more important because in real case, maybe you always do have an initial condition. But the point is that if your controller is, your system properties are well defined, you can really consider that initial condition to be a disturbance. Right. So, in point of fact, in optimal control, we do not consider the question of an initial condition other than 0. Now, there are variations of this in the literature, right? I think not many, but there are a few. So state to output properties, right? Again, right? It's not something that's very well developed because really, there's no way of predicting what the initial condition of your system is going to be, right? In practice, right? It could be in any state. You can't really assume that it's 0, but you can't really assume it's anything else either. So, we very importantly will throughout the rest of this lecture assume that this is 0. If it's not, right, there's an extra term here, which is the solution becomes there's a CE to the ATX naught term, which also pops in. But we again are going to ignore that. So anyway, building up to that, right? Likewise for the discrete time system, there's an explicit solution for the system, and here the e to the at term also becomes, this is the equivalent of e to the at x of 0, right? But for our purposes, again, we're going to cross off those terms and more or less ignore them. So for a discrete time system, there's also a solution. You can verify it's a solution relatively, actually a little bit easier. You don't need the Leibniz rule for differentiation of integrals, which is just a summation. So you replace the integral with a summation, and this is like similar to e to the a t minus s kind of thing there. Just replace the integral with the sum, a finite sum. Yeah. And so again, right, if we just focus on this term, right, there's a relationship between the inputs and the outputs, which doesn't depend on the state in any way, right? We've eliminated the state. And here again, we usually take x naught is equal to 0. Right, so that was, in a way, the easy part. Now we get to something which is a little bit more complicated, right? So, which is definitions. Well, you can't prove any, you can't have an argument if you don't define what it is you mean by various terms. And so we have to very precisely denote what we mean by controllable, stabilizable, reachable, these terms. Right? Highlight them here. Reachable, controllable. Now, what's funny, of course, is that reachability is actually defined twice, right? So, so in particular, they're both defined sort of as an input to state map, right? Here's your input. Here's your state. So let's go over this one first, right? This is defined in terms of the map. This map from input to state. And we're going to use this term gamma here going forward, which maps this input to the current state, x of t. And this is from the previous slide, of course. So reachability. So what I sort of motivated this question on the previous slide. Reachable. Well, we say a state is reachable, which is different than a system being reachable. So this one is the property of the system. And this is property of the state. All right, so we say a state is reachable if there exists an input signal, of course defined on a fixed time here, tf, right? Because what does it mean to be reachable if you never actually reach the state? So on a fixed time, right? So this state is reachable if there exists an input signal whose solution, right, the corresponding solution, reaches that state at the appropriate time. Right? So it reaches your desired xf at time tf. And this has to be true for any fixed time, right? It's not difficult to show that if it's true for some fixed time, it's true for any fixed time, but that's another question for another slide. But in any case, so what we're saying is that a continuous system, for a continuous system AB, defined by those two matrices, the state is reachable if for any fixed finite time there exists a signal which will drive you to that time, to that point. Well, actually, this is for any fix, not for, there exists some, there exists for any time. Right? So starting here, let's just assume it's x naught equals 0. Right? In a desired point, xd, let's call it, there exists an input signal which will drive you there. And if you want to get there faster, there's a signal which will drive you there faster at any desired speed. So this is, say, tf equals 1. This is tf equals 2, for example. And then, of course, that applies to tf equals 0.00000001, for example. Right. So that's reachability of a state. So we can get there. Right. A second notion of reachability is that of a system. So the system, AB, parameterized by those two matrices, AB, is reachable if you can get anywhere, basically. If any point is reachable. Right. So that's not hard to see. Given an xf, right? If that xf is reachable, and we can change that xf arbitrarily, then the entire system is reachable. Right? So reachability of point, any individual point, and this is reachability of every point. One point. This is every point. Call it XD for desired. Right. Okay, so there's two notions of reachability. One of a particular state and one for every state. So this is more of a property of the system, less like fussiness, right, of individual states being reachable or not. Next, we have this somewhat counterintuitive notion of controllable. So a system is controllable if, again, for any fixed time, right, and any initial condition, right? And here we're sort of relaxing the condition that x of 0 equals 0, right? Although it doesn't matter, actually, it turns out. There exists an input signal which will drive the system to 0, right? So we assume in this case x of d equals 0. So that's a little bit different, right? It says that we're starting somewhere else. Call it x naught. And we want to be able to get to 0. Well, that's actually a little bit easier, of course, because even if you can't control some states are naturally stable. So that seems like it would help. But the problem with that interpretation, that's actually the stabilizability interpretation, which we won't go into quite yet. We'll get on to the next slide. The difference there is this finite time. Finite time. So we can't just let it slowly decay to 0. It has to reach 0, right, in fixed time. So input signal drives us to somewhere, but it drives us there to here to 0 in finite time. And the finite time has to be able, you have to be able to choose that arbitrarily. That's not a problem, again, because these are linear systems. We'll come back to that in just a second. Right. So actually, well, I guess we're going to come back to it now. So we'll motivate this more in the future, or in the next slide. These sets, right? The set of states which you can reach, right? The set of states you can reach it from, right? Are subspaces. What is a subspace? Well, it sounds like something from Star Trek, but it's really actually not that complicated. It's just right. It's a space. It's a set of points which satisfies certain linearity properties. And so you've probably worked with this in matrices quite a bit, and so we'll just do a quick refresher on it, and hopefully that'll be clear. Again, right, we're going to be talking about it in terms of this map from inputs here to states here, parameterized by this time tf here, right? And so I just want to emphasize right here in this little colorful blurb that there's a map, right, gamma, which maps this signal. You can think of it as a system itself, which maps this signal on a finite fixed time to the state at a fixed time. So it's not really signal to signal, it's like signal to vector. But so you can think of it as a system itself. And the key property is that this map is linear, right? So if you double u, right? If you double u, if you use your input to u of t, then the output is to x of t, right? Because I mean, you just plug 2 in here, and well, this is just multiplication. There's just integration, so you just like plug 2 here, and then I could just move 2 over to outside the integral, right? And so we get 2, right? So if you can get to x of t, right, you can get to 2x of t just by doubling the strength of your input, right? And this linearity property is important because it sort of undergirds the rest of the slides, really. So before we talk about subspaces, right, we need to define a space, right? And what we mean by a space is a vector space. Right? A vector space is these are the same thing. So before we talk about a subspace, like a smaller one, we want to talk about a space itself. And so what is a space? Well, by space we mean vector spaces. And basically, a space is a set, right? A set of points. Set of points here, which satisfies certain properties. Remember we talked about the convexity property, right? Where if you joined all this together and colored it in, right, then that's the set itself, right? So that was the convexity property. Here it's actually a little bit weaker, right? It basically says if you take any 2 points in those spaces, if you add them if you add them together, it's also in the space. Not just a convex combination of those 2 points at any coefficients alpha and beta, right? Where those are in R, not positive coefficients, they can be negative coefficients. So if this point is in the space, right, all the coefficients down to 0, all the positive coefficients, and actually all the negative coefficients as well, also have to be in the space. And so if you have 2 points now, right, all of those, right, these are the scaling properties, have to be in the space. And the addition of all of these points in these 2 lines have to be in the space. So basically all of these points plus this point, right? So all of those points. And of course you can have negative coefficients, so have to go that way as well. So basically in 2 dimensions, right, if you have 2 points, right, everything. So a subspace or a space, right, is basically the mathematical foundations for what we're doing here. You can have vector spaces of signals. The vectors are themselves a vector space, obviously, Euclidean norm. And of course, matrices are a vector space as well. Okay. So you can add them together, scalar multiplication, so is multiplying by those scaling factors. So if you scale, then you scale the sum of 2 points together, it multiplies out, and that point also has to be in the space. And then, right, you add two scalar multiples together, also in the space. Now, okay, so that's a space. It's the most sort of basic tool we have in analysis, and it really only has to satisfy these 2 things. So if you want to test if your space is a space, check these 2. If it satisfies them, it's a space. If it doesn't satisfy them, it's not a space. Right, so given the definition of a space, then, well, what is a subspace? Sub indicating it must be smaller than a space, right? But be careful with that because it's a subspace of a vector space. So given a vector space, we can define subspaces of the vector space. So subspace of a vector space is any subset of that vector space. So for example, the picture maybe you want to draw here, right? Here is R2, right? So what's a subspace of R2? Well, okay. Suppose we have a point in R2. Well, if we just apply these 2 properties to that point, right? Well, a subspace has to satisfy those 2 properties, which means this entire line in both directions, infinitely far in both directions, is in the space, right? So do we have to satisfy anything else? No, right? So if we want to define a subspace based on a single point, right, this is sort of a minimal subspace of that vector space. Right. The subspaces you're probably most familiar with, and I do assume you've taken some courses in matrix algebra here, and that was sort of a requirement for the course. The 2 you're most familiar with, I don't know the quality of the course that you've taken, but The two subspaces that we consider most often, or we find most often, are those associated with matrices, right? So matrices are linear maps. Y equals mx, right? A map from a vector to a vector, right? And so, well, what are the two subspaces? Again, they have this weird name, kernel, right? Image is fairly clear, but the kernels, I don't know where they got the name kernel. So there's two subspaces associated with matrices. The first is the image, which is a little easier to picture, but maybe harder to quantify or define or something like that. Actually, maybe it's harder. I don't know. See, the name is at least more intuitive. And that's a set of points you can get to, similar to the idea of reachability. We'll stretch that metaphor going forward. So it's a set of y's for which there exists some x such that y equals mx, right? X in Rn, so vector space, such that x equals my for some y in the sort of the preimage, right? So this is a matrix M of dimension n by m. Right. So the image then is a set of points y or x. Sorry, I'm mixing up I should be reversing these here. Right. The set of points x for which there exists a y such that when you multiply it by m by y, you get x, right? So it's the image, right? So you've got your x's, and x, right, is the whole y is the whole Rm, right? So if you've got m here as a system, right, you're sort of spraying it with Rm, and then what comes out of it, right? Well, that's R in Rn, but that's the image. So you think of it as a projector. You have light going in, and then what's coming out is the image. Okay. So the opposite of that idea is the kernel, right? So that's the kernel. The kernel is the set of vectors x which get occluded by m, which get blocked by m, which don't produce any output. Right, so if we think about it, that same projector metaphor, right? We've got a set of things going in, which is the kernel of m. They go into m, and they get blocked, right? They just produce zero output. Right. So two different ideas, right? So actually, I guess the first one would be more appropriately modeled. It's like if we're doing our projector metaphor like that. And this is Rm, right? So the kernel is a set of x's which get blocked by m. So the set of x's for which mx is just equal to 0. Yeah. So there's two subspaces. Obviously, they satisfy the properties of subspace. You add a multiple of, you scale 0 by any multiple, it's still 0. And likewise, right, if x is in the image, right, then alpha x is in the image because, right, you just scale y by alpha and you get something in the image. Right? So fairly straightforward. Okay, so right, these are the key subspaces when considering matrices. Yeah. Now let's see if we can extend that to some extent to systems, right? And see if there's any parallels. So this is a system which we sort of write as gamma t, right? And we're looking at the set of inputs, right, which will spray into our reachable set. So our set of reachable x's. And I guess I should make that TF right there. Right. So first of all, right, a key property, right, is defining this reachable set, right? So this is RT, right? And so this is the set. This is like the image of gamma t. So the set of outputs, the set of states for which there exists some input which gets mapped to that x, right? So this is very similar to the idea of the image of a matrix, right? And like a matrix, right, this gamma t is linear, right? Key point, right? We talked about that on a previous slide. That this is a gamma t which is linear. And so this reachable set, right, this image of gamma t is then by definition a subspace. Well, I don't know by definitions, but it's an obvious corollary that this reachable set must be a subspace, right? Because you can scale the input and it just scales the output. So subspace, you can add two inputs together, right? And it's just the sum of the outputs for each of those individual inputs. Right? So if we get our system here, and we get u plus y, right? The output is gamma t u plus gamma t y, right? Because it's a linear system, right? So that's a set of reachable states. Important subspace. Now we define two others. So this is defined in terms of the properties, right? Of the map, of the system map. Next, we define a different subspace. So remember, we talked about image and kernel of a matrix. And now we're talking about image of an operator of a system. And so we're gonna bring it back to a subspace of a matrix and see if we can somehow relate the two. Okay. So we do that through a special matrix called the controllability matrix. Right? So the controllability matrix is, well, it has its own little special symbol here, highlight, which is this thing here. And yeah, again, right, many of you have seen this in 506. If you're taking 506 now or if you've taken it in the past, you've seen this controllability matrix, I'm sure. Right? And it's just a function, I guess you could call it, of the system representation A and B, right? So it's a function, right? So that's why it's written sort of like a function, where you put the B in the first spot, right? So B's, remember, are generally look like that. They're sort of skinny, and in the second slot, we multiply that B by A. So B is sort of like the set of states which are initially influenced by U, right? So BU. Yeah. And then we get the set of states which are sort of influenced by BU, but indirectly through this A matrix here. Right? So we have this BU, which is still skinny, and we multiply it by an A, but of course that the result is then still skinny, right? And so it's the inputs go to get mapped to some states. I should write down the x dot equals, remind you what the system is. Yeah. So these inputs get mapped, right, to the dynamics of a certain set of states initially, and then they get mixed. They get mapped to those states, then get mixed up through the A matrix, right? Get mapped U. First column gets mapped to x dot, and then that gets mapped to the second column, which gets multiplied by A, and then those states then themselves get mapped back, mixed up further through the A matrix again, through A squared, and then they keep mixing and mixing and mixing until you stop mixing, right? And that's you stop. How far do you have to go before you stop mixing? Well, if n is the dimension of x, right, X is in Rn, right? You stop mixing, well, it's also the dimension of A, right? A is in, see here, A is in n by n. You stop mixing when you get to A n minus 1. So there's only n terms in here. And then, of course, the key question then, why did you stop mixing at n minus 1? What happens if you mix it a little bit more? Well, we'll talk about that in the next slide. Okay. But anyway, this is the definition of the controllability matrix. This is what it is. It's another matrix defined by, sort of an intermediate matrix defined by the system representation matrices. Right. Okay. So that's all good. So that's a matrix, right? No properties of the matrix yet, no vector spaces or anything. And so now what we do is we take that intermediate matrix and we define, well, sort of intermediate vector space, which is the image of that matrix. So the image of that matrix. So on the previous slide, we defined subspace, which is the I don't know, we did X equals CA B U, right? It's a set of X's which you can reach through this matrix, right? And this is a subspace defined by the matrix. And again, we'll consider it doesn't have any physical meaning at this point. It's still an intermediate subspace. Right. So it's an intermediate subspace. It's not this subspace, which is what we're actually after in the end, but it's at least defined in terms of matrix properties. And, you know, MATLAB can find it. There's no way MATLAB can do anything with this thing up here. But MATLAB can find the image of a matrix, and so you can, we're on more solid ground dealing with this. We can figure this out. Unfortunately, over the course of this point, it doesn't have any interpretation until we use this very important theorem based on the Cayley-Hamilton theorem or something like that, which says that the controllable subspace, right, is equal to the image, well, which is natural, of this matrix. So this is just a definition, right? That's what we're defining. It's defined here, in fact. But this very powerful theorem says that the system is controllable, right? So the set of states for which we can drive the system to 0 is all of Rn if and only if the matrix here is full rank, basically if the image is itself Rn. Right? It's a very important relationship between this property of a matrix and this property of the system, or property, I guess, of the map, gamma. Right. Now I don't prove these, right, because this is in this class, right, we don't have time to prove all the theorems, and you'll see it in 506 if you take a different class. But we're going to use that property, that relationship between these two vector subspaces, right? Right, so again, I think we're just restating what we have here, right? Yeah. And the reason you could stop after n is this very important theorem, Cayley-Hamilton theorem, which says basically you could stop after n steps, right? It's why we don't have a to the n be here. We don't need it. Cayley-Hamilton says so. Cayley or Hamilton. I don't know if that Hamilton is like, which Hamilton that is. Is that the same Hamilton from the Hamiltonian? I should look that up. All right. Okay, so now we've got the system properties, map from input to output, which is encapsulated by gamma. Well, actually, we're just doing state at this point. In terms of that system representation, which we use to construct A and B. And now we're going to relate that to an LMI, right? Or a positive matrix. So LMI / Lyapunov function / positive matrix. Right. And so that'll allow us in the future, of course, to sort of bypass that internal step here, right? We'll ignore this step in the future, and we'll just be able to relate an LMI directly to system properties. This is an intermediate step. Right. So what's the Lyapunov function, which gives us this system properties, and how do we show it's a Lyapunov function, right? So it's actually not that significantly different than the one we had for stability, right? So if you remember the one for stability, right, it was integral e to the a transpose s e to the a s ds 0 to infinity, right? That was the p for stability. Right. So what's different in this case? Well, remember what this was, right? This was a map from initial condition to, initial condition to, initial condition on the outside to x of t, right? So this, then we have, that becomes, this whole integral becomes integral of x of t squared ds, right, or dt. No, I'm good. Yeah, so in this case, well, there's a couple distinct differences, right? We've got the transpose on the wrong side, and we've got a b in the middle, right? And basically, what this comes from is we're looking at the inputs basically go in the middle, right? So basically, we could choose anything in the middle, right? So these inputs get mapped to through this function here to the state, x of t. And so we want to sort of determine which sets are reachable through some proper choice of this intermediate u that goes in the middle. So that's I guess that's a good way of thinking about it, right? Again, somewhat similar to what we had in the stability case, but not exactly. So okay. That's the idea. Well, obviously, if you define a W in this way, it's a positive semi-definite matrices. Why is that? Well, I mean, you multiply it by x on both sides, x transpose whatever that is, right? And then it's symmetric here, right? This becomes, right, something transpose b transpose e to the a transpose s x, right? And then it's the same thing on the other side, and so it's a square, and square is positive semi-definite. So we integral something which is positive semi-definite. It's always positive semi-definite. Right. Right. So this is the sort of the set of ways that you can produce x, right? And so obviously, if this has a zero eigenvalue, for example, or if it's zero for some, it's not positive definite, right? There's some set of x which you're not going to be able to reach through this intermediate u, right? And so that's the idea of this w. Right? Theory-wise, right, we have this very powerful result, which takes a very long time to prove. And in my 506 class, when I occasionally teach it, we actually go through the proof. In this case, I'm just going to state it, which basically says that for any t, and this is come back to that in a second, right? It's very important for any t, that basically what I just said, that the image of this matrix, this positive matrix, positive semi-definite matrix at this point, is equal to the controllable subspace, which was defined in terms of the representation, intermediate step, which is equal to, and we mentioned that on the previous slide, the reachable subspace. So system property. Right. So a relationship between this particular matrix, right, if it exists, and this intermediate step, which we don't care about, and the property of the system. Right. So we've now been able to skip this intermediate step entirely, and just these two are equal to. Those are the ones we really care about. Now, why is this interesting? Why do we even have the intermediate step, in fact? Well, it's important. That's where the for any t comes in, right? So remember, reachable set is like the set of states we can reach at time t, right? So it's a subspace and for a fixed t, right? So this is defined for a fixed t, right? And our image, right, of that system map from input to state is for a fixed t as well, right? And this Grammian, the controllability Grammian, right? This is the finite-time controllability Grammian. So I don't really emphasize the controllability Grammian part here, but it's a finite-time controllability Grammian. So it's a finite integral, right? Right. So these are related. Where this is a finite time integral, this is defined for finite time, this is defined for finite time. But this is not. T doesn't appear in the image of this matrix, right? And that's why it's so important. Because what this says, basically, is that, well, it says several things. Importantly, it says that if this Grammian is positive definite, right? Positive definite property of a matrix greater than 0, right? That implies that the image of the matrix is Rn. Right? If that image is positive definite for any t, right? Then the system is controllable. That this image that the system is controllable. And likewise, right? If the system is controllable, then this matrix is positive for any t, right? So we don't have to actually like check this for every t. We only have to check it for one t, and we can choose whatever t we like, right? Wt. So that's a very powerful result, which says that the controllability or the reachability of a state doesn't depend on how much time you're allowing it to get there. If you can get there arbitrarily fast. It doesn't matter, right? Reachable set does not depend on t. And so that's a very important result. So we're not going to go through this proof. The proof is rather complex, and there are parts which are not particularly illuminating. But we are going to go through one bit of it, right? So again, it relates the properties of the representation, properties of the map, gamma t, or the system, and an LMI / Lyapunov function. Okay. But I think it is illuminating, and then we'll actually use it on the second part of this lecture to go through one particular part of that. Right. So remember we proved that all three of these are equal CAB, which is the image of CAB, and make sure you don't get those confused. Right. This is CAB, which is a matrix, and this is a subspace, right? So C sub AB is a subspace, and this is a matrix. Right. Yeah. So don't conflate CAB and C of AB. Right? Anyway, so we have to prove that all three of these are equal to each other, and they're all sets, right? Because there's an image here, this set. And how do we prove that? Well, basically, it's a very complex step, right? We have to show if X, so this is a third one here. So if X is in this space, so basically it's a circle. We show if X is in this space, then it's in this space, so that this relationship holds, subset relationship. And then if X is in this space, it's also in this space, and if X is in this space, it's also in this space. Right? So basically, if X is in any one of the spaces, it's in all of the spaces. So that's the proof structure. We're actually only going to go through one of the steps, I think the most illuminating one and the most useful one, which is as X is in this image, right? That implies, therefore, X is in RT. And it's illuminating because it actually gives you the input which drives you to that particular state. So we can plot stuff and things like that. And the proof is rather short. Right? It's short because we know what the answer is. Someone came up with the answer. Right? So suppose that X is in this image of this matrix. Right? Remember what W was. W is like T is integral from 0 to T of e to the a. Wait, make sure I don't mess this up. AS, yeah. Okay. B transpose e to the a transpose s ds. Right. That's what W was. So just box that off. Right. So anyway, it says if X is in the image of that matrix, right, then remember what the image is. Then there exists a Z such that X equals WTZ. Right? WT is invertible for that X, basically. Right? We could find Z equals WT inverse X, right, for that particular X. Now, WT may not be invertible for every X, but it has to be invertible for that X. Right? So we can construct this Z as such. So suppose that that X is in this image, right? Then there exists some Z. There exists, in math notation, this is backwards E for there exists a Z, such that X equals WT, Z. Right? And so now propose this input signal, right? Again, I don't say it's a function of time. This is an input signal. We propose this signal. It's a function of S, right? Doesn't matter what the dummy variable is. I don't use T because T is already here, right? So it's like a different T, right? So be careful there. So it's a signal. It's defined for every S in 0T. Right? And then the only thing we need to show is that it produces, or it arrives at our desired state, right, in the required amount of time. So let's just look, right, at the output from that signal, right? So this is, remember, the map from gamma t. This is the map from u to x of t, right? Finite time. So that's the map. That's what it is. Just recall that. It's from the solution convolution integral. And so now we just plug in for u. Right? We take this u here and we just plug it in for u of s. And then it becomes this thing right here. Right? So now we plug it in there. Right? And well, what do we have here? Well, okay, we've got an extra z here. But this should look familiar, right? We're just going to move that delta ds there. And then this big thing here, right, is this big thing here. Right? This is just WT. Right? And so it's just WTZ, which, of course, by assumption, right, or by the definition of image, is equal to x. Right? And therefore, we conclude, right, that x is reachable at time t, and hence it's in the reachable subspace. And hence, therefore, we conclude that if you're in the image of this controllability Grammian, finite time controllability Grammian, you are reachable. Right? Now, why did I bother proving this? Well, A, it's short. And B, it gives us actually a very useful piece of information, which says that if you have a desired state you want to reach in finite time, say at TF, right, it gives us the explicit solution, the explicit input signal. It's an open loop control signal. I emphasize open loop just so it's not, you don't think it's closed loop, which will drive the system to that state. So specifically, right, it's this z. Well, okay, we got to figure out what z was, right, because we assumed it exists because it's in the image. So it's the inverse of w as applied to that particular state. Now, it may not exist for all states, but it has to exist for that state, right? So as I said, w inverse, this is z, right? And then, right, just plugging in the our u over here as well. Comes down here. And so that gives us a time signal, which for zero initial condition, of course, we assume that, we have that the final state at time tf is the desired one, right? The solution to the differential equation achieves that desired state at the desired time. So this says if we can solve this Lyapunov function, not only does it tell you things about the system properties, but it tells you everything you need to know about how to get to every state in the entire reachable space, which is really quite remarkable. So we can just this is a very useful thing. We can implement it in MATLAB, and it's nice to have something useful at this point, since there's a lot of theory going on. And so, for example, here's a mass spring. This is from Sanjay's lecture notes. We'll construct lots of mass spring systems later on. Basically, this is the inertia term, right? We're declaring a new set of states. These are x, right? So these are the equations of motion, right? I'm not going to derive them, obviously, because, right, I think we're beyond deriving mass spring systems. I think probably you've seen them in high school, hopefully. But in any case, this is a state space formulation of that system. It has one input right here, which occurs, well, what does that occur? That occurs, looks like here at the first state. Right? No, actually it occurs, looks like it occurs here. Right. Oh yes, applies to mass 1, it says so right here. Right, because there's a 2 here and there's a 1 here. This is the end spring. End mass. Right, and so we have we got some damping constants, spring constant here. And we desire to reach a particular state, somewhat arbitrarily chosen as 1, 2, 3, because why not? And also, don't forget, we have, these are our velocity states. So these are x of t's, and these are x dots of t's. Right. So our velocity we want to be 0, and we want our actual states to be 1, 2, 3. So we want to get to where we're going and then be not moving when we get there. Of course, if you then let it go, right, it'll oscillate all around. But assuming you hold it there, then you can keep it there, right? And we want to do that at exactly t equals 80 seconds. Well, how do we do that? Well, we solve for wt, right, integrating that term numerically. And I think actually MATLAB has an expression which will do this for you. And then we find that here's our desired, right? z equals w t inverse x80, right? And then we use that to get our input signal u of t using the formula on from right here. And actually, we got it better form. No, okay, good enough. Oh yeah, right here. Right. Use that formula there to provide our input. And we plug that into MATLAB using LSIM. We'll talk about MATLAB a little bit more later. Using LSIM, and that produces the output which we see on the next slide. Right. And you can see here, here's our single input, right? A single input to a single force to one of the states, which will drive the system. It sort of oscillates for a while and then gets over here. It'll drive all those states. It sort of fluctuates, makes them vibrate a bunch. And then they all go at the desired time to exactly where they're supposed to go. xi dot equals 0, and x1 equals 1, x2 equals 2, and x3 equals 3. Right, as if by magic. Right, and of course it's not magic, it's control, and of course it's control. It's not going to work very well because it's open loop and all that. But, you know, for people who don't care about such niceties or subtleties, it seems sort of like magic. Right. Okay, so that's a good stopping point, and I've probably exhausted my my stamina at this point, so I'm going to stop the recording, and I'll join you again soon.